sheet with prefixes. We're talking about covalent compounds. These are going to help us name our covalent compounds. In covalent compounds, molecular compounds, we use prefixes. All right, the first thing that we're going to talk about is naming molecular compounds. And specifically, we are naming binary molecular compounds. This means that we only have two different elements. So this is a binary compound because we only have nitrogen and oxygen. There's only two. How do we know that this is a molecular compound? Perfect. These are two nonmetals. That's our requirement for molecular compounds. Okay. So this is how we name them if they don't have hydrogen. Okay. So we are going to use a prefix and then the first element name, and then a prefix and then the second element name. The second element name we change to I, just like in ionic compounds. Okay. So we're going to say prefix. The prefix is on this sheet. Okay, the prefix tells us how many we have. So if I have 3 of something, that's going to be tri. So this one here, we use our prefix di because there's 2 nitrogens. So I can look, there's 2 nitrogens, that's prefix is di. The next one I need to figure out 5 is the prefix is penta. And this is oxygen. I changed the second element to I. So this is dinitrogen pent oxide. We're going to talk about a rule if we have a vowel at the end of the prefix and a vowel at the beginning of the element. We're going to drop the vowel at the end of the prefix. Okay, question so far, we're okay? So this is our rule for naming molecules with only 2 elements, as long as it's not hydrogen. Okay, we're just going to keep running through some of these rules. Okay, so here are some, we just talked about this rule. If a prefix ending in O or A, so that would be mono or penta or tetra, okay, lots of them end in A or O. If you put it next to an element that begins with O, drop the O or the A from the prefix. Okay, this only basically happens with oxide. So here's one example where we don't drop the prefix. So this is carbon tetrachloride. We keep the tetra. This one is dinitrogen tetroxide. So the tetra has an A, oxygen has an O. We drop the A from the prefix. Okay, we just don't want 2 vowels, one in the prefix, one in the element. We want to drop that from the prefix. Yes?
So there was a confusing topic on relics. There was like 3 iodine or something. So it was like triiodine. Do you just keep all those vowels then in that one since it's
Yes, because it's not an O. Yep. We just mostly care about oxygen here. Yep. Good question. Okay, here's the second rule. If the formula unit contains only 1 atom of the first element, the first prefix is left out. So we never use the prefix mono on the first element. Okay, so let's look through our examples. This we have 1 nitrogen and 1 oxygen. So this is just nitrogen, not mononitrogen. This is just nitrogen monoxide. And also notice we dropped the O, okay, on the mono. So nitrogen, the second element always gets a prefix. The first one only gets a prefix if it's more than 1. Okay, so here's another one. We have 1 nitrogen, that's our first element. We have 2 oxygens, so this is called nitrogen. So it doesn't have a prefix because there's only 1 of them. Dioxide. Okay, nitrogen dioxide. And then if it has more than 1 element, more than 1 of the first element, then we start using prefixes. So the third one here, we have 2 nitrogens, we have 3 oxygens, so this is dinitrogen, trioxide. This one we have 2 nitrogens and 1 oxygen, we still put the monooxide. So dinitrogen monooxide. Okay. So the second element always has a prefix. The first one only has a prefix if there's more than 1. Questions so far? We're doing okay? Okay. Okay. So go ahead and, with your prefixes, go ahead and try to name these compounds, these molecular compounds. I'll give you a minute.
No, not arsenic.
Yeah.
Bromide. Yeah, it's. Is this yours? How would you do that? Take it.
Okay, 10 more seconds.
Yeah, where is it? No, no, T. I can't speak to her. Wait, you need to. No, I'm good, I'm good, I got it.
I always have to pee in this class. Like, I don't know what it is, but I don't want to miss anything, I'll just go off with this. I'll just hold it.
Okay, let's go through a few of these. I know you probably didn't have time to get through all of them, but hopefully you'll practice this more on Alex. Let's see, how about this one? What would you call this one? This one. Good. So we don't capitalize it, that's a T. Okay, and then we put a space. and then tetra. Oops.
Oh, we don't capitalize it.
No,
What about the third one?
don't capitalize it. Tetrachloride. Okay, we don't put a space between the prefix and the element. They stay together. No space. There's a space here though. Okay. Third one here. How about this one? You said this one. What's this one, Sebastian? Did you ask for this one?
Yeah, I was asking if it would be chloride or chlorine.
Oh, it's gonna be chlorine.
Okay.
Yep. So the first one we don't change the ending. Good. So it's gonna be di chlorine.
Heptaoxide, right?
Yep.
Got it.
Space. That's a space. Oops. Space penta. Not penta. Hepta. Excuse me. I get hepta and penta mixed up. Move. Oh, this will get out more obvious. Hepta oxide. Okay, what are we gonna do here? We've got hepta oxide. What should we do? We good. We need to drop the 8. Okay, good. All right. How about this one?
Nitrogen triiodide.
Space. Triiodide. Okay, good. We're gonna keep both of those I's. Good. Okay. All right. You can practice more. And Alex, go ahead and do it backwards. So if we have the name, what is the formula?
C5H6O5 POS2O7 AS2S5.
Okay, are we doing okay? You guys got this? You want to go over any together?
Yes, please.
Okay, do you want to pick one for us?
The first one.
First one, okay. Boron trifluoride. What will our formula be? Good. Okay, this is an example where boron, if we draw the Lewis structure, boron only has 3 bonds. Okay, that's one of our examples where boron only has 3 bonds. Okay, how about this one? What would this be?
Should be sure.
Sorry? Okay, 2 sulfurs. The hept means 7, so 7 oxygens. Okay. Alright, so that's another one of our Alex topics. Okay, this is a little different if we have hydrogen. So if we just have hydrogen, then remember, hydrogen fits between the nitrogen column and the oxygen column. Okay, so it's still going to fit there. But we're going to name it differently. If there's only hydrogen and one other thing, then we're going to name it like an ionic compound. We don't use prefixes. Okay, this is an exception just for, yes, if it has hydrogen and one other thing, then we're going to use these naming rules. We're going to name it like an ionic compound where hydrogen is the cation. So here are 2 examples. We have HBr. We recognize we have hydrogen and something else. So we're going to use this rule. We're going to call it hydrogen and then bromide. Okay, so that one's not too bad, but we don't use prefixes, okay? No prefixes. The next one, we have 2 hydrogens and 1 sulfur. This is going to be called, because we just have hydrogen and one other thing, we're going to call it hydrogen sulfide, no prefixes. Okay, this is just like an exception. Like most of chemistry is exceptions. We make rules and then we write exceptions. Okay, questions on that? All right. Okay, I see a few pencils writing, so we're gonna wait for just a minute. Okay. Go ahead and name the, let's just name it together, so there's only 4. How about this one? What would we call this? We have hydrogen, something else?
Chloride.
No prefixes. Hydrogen chloride. Okay, how about this one?
Hydrogen phosphorus.
Good. How about this one?
Hydrogen selenide.
Hydrogen selenide. Good. And the last one?
Hydrogen iodide.
Good. Okay, these are 2 compounds that Alex wants you to memorize. We're not going to call them by their systematic name. That's what we were just doing, systematic naming. We're going to call them by their common name. So hopefully we already know this one. You've already have this one memorized. When it says, what is this called? You're going to call it water. This is another one. You might have seen this before. We use this in the lab a few times through the year. Yep, so NH3. We're not going to call that by its systematic name. We're going to call it ammonia. Okay. Questions. Ammonia is NH3. Sounds like there's somebody walking on the roof. Okay, so these 2, when they come up, you're not going to systematically name them. You're going to remember, that's just water. I know that one. And then NH3 is ammonia. Okay, you got it? Okay. All right, so we're going to go over our exceptions to the octet rule again, because we're going to start talking about shapes, and this comes into play. So the first exception is hydrogen only wants 2 electrons, just like helium. Okay, that's an exception to our octet rule. Group 3, so that's boron, basically just boron, sometimes aluminum. They want just 3 bonds. Okay, they can only fit. This is supposed to be 3 bonds. Okay, I'll fix that. I haven't fixed that yet. They want to fit only 3 bonds. So that's up to 6 electrons. And then remember, period 3, that's the 3rd row. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur. If we're in that row or below, those atoms can fit more than 8 electrons. They're big enough. That is an exception. You're not going to have to draw those, but the shapes that we're going to look at, some of them have extra electrons. Okay. Questions so far? We're doing okay? Let me grab out our note paper. We're going to talk about these papers next. Does everyone have these papers? Okay. All right, I don't see anyone writing. We're going to move to the next slide. So we are going to use this theory. We're trying to figure out the shape of molecules. This is called the Vesper theory. And the basic concept of this theory is that electrons repel. Okay, and you probably already know that, right? Electrons are negatively charged. If you have a negative charge and a negative charge, those are going to repel. So we call this the Vesper theory. It's called valence shell electron pair repulsion. So the electrons in the outer orbitals are going to be repelled, and they're going to try to go as far away from each other as they can. And that's what gives us these shapes. Okay, you have 2 different examples of what we're talking about. So as you're going through, you can look at either of these papers. So if somebody's talking about the Vesper theory, this is what they're talking about. This is what they're talking about. The shape of molecules. So this is something that is in 3D space. So you have a molecular model kit in front of you. This one's help us model these 3D shapes. So we're gonna go through and we're gonna model these shapes here. Or we're gonna model these ones. That's what we're doing. So we'll go through them together. First, we need to know what an electron domain is. So an electron domain is where the electrons are. Electrons can live in a bond, or they can live in a lone pair. Okay. So if we're looking at this molecule, what's this one called? NH3. What's it called? Ammonia. Good. If we have NH3 ammonia, yes. Yes. You're all saying. If you have NH3 ammonia, how many lone pairs are there? Sorry. How many bonds does ammonia have? Good. And then how many lone pairs? One. Good. Okay. So how many total electron domains does ammonia have? Has one in a bond, or excuse me, 3 in a bond, 1 in a lone pair. How many total? 4. Okay, so this counts as 1 electron domain, 2, 3, 4. So when we're looking at if we look at this one, the electron pair geometry, we look for something with 4 groups. 4 electron dense areas, 4 electron domains. So what shape is that if you have 4 electron domains? So 2, 3, 4, that's tetrahedral. Okay. You can also look up at this across the top here. So this is electron pair geometries, and we're looking at just the electrons. We either have 2, 3, 4, 5, 6. So if we have 4, that's called tetrahedral. Okay. All right. Oh, okay. First, look, I forgot. Our models are just in a minute. How many electron domains for the selected atom? So okay. So you want to go through. So how about oxygen? We've got 4. Okay, 4 electron domains. How about selenium here? Good, 5. This is an exception to our octet, but it's okay because selenium is below the third row or below. We've got 1 lone pair and 1, 2, 3, 4 bonds. Okay. How about phosphorus? How many? Good, 6. We're just looking at the central atom. Phosphorus has 6 bonds, so 6 domains. How about this one?
3.
Good. And then how about this oxygen? How many electron domains? 4. This one's tricky. This is 1 bond. The electrons are living in this bond. So there's only 2. This one only has 2, okay?
So
Yep.
like 6 electrons in the molecule in that like
Yes, 2, 4, 6. Yes, there's 6 electrons in that triple bond. Yeah, good. Okay. All right. Let's go ahead and look at our shapes now. So we have, this is like to hold your structure that you built. So I'm just going to go through and build some structures. So the first one I'm going to build is linear. It needs 2 electron orbitals. I don't care which one you pick. I'm going to pick this pink one and this first one. It doesn't really matter. So if I have 2 electron groups, or if I have just 2 atoms, it's going to be a linear molecule. Okay. The furthest away these electrons can repel from each other is 180 degrees. So this bond angle is 180 degrees. Okay. They're not going to be 90. They're going to be as far away from each other as they can be. That's linear. Okay, the next one that I'm going to make is with 3 bonds to the central atom. So like 4 trifluoride. So I'm going to find the atom. Some of them have a little hole in the corners. So look for one that you can make have 3 bonds.
what is that?
So look, one has like a corner bond. So you want to try to do
This is a Lego.
1, 2, 3. Okay. So This is as far as the bonds will go. This isn't exactly our bond angle, but it's pretty close. So what would we call, or what would our bond angle be on that? If we have three different groups around the center line. Good, this is called trigonal planars. Trigonal, we got three groups. Trigonal, it's in a plane, planar, okay? Trigonal planar. Our bond angle is 120 here. So we just take 360 divided by 3. That's 120. They're as far apart as they can be if they're at 120. Okay? So that is our, if we have 3 electron domains. Okay, the next one is 4. For the 4 electron domains, you have to find the atom that has like, it's not on the, not like a dice. It's like, this one's for 3. For the dice. Yep. So yeah, 1 for 4. Yeah, I know it's not exactly. That's good. Okay, so if I have 4 groups, I'm gonna put the 4th group on the trigonal planar, but this 4th group pushes the other groups down. So I'm gonna put 1 color and then 3 colors to show you. Show us sort of kind.
How'd you do that?
Okay, so this one, I have 4 groups. This is called tetrahedral. So they're gonna try to space as far from each other as they can. If I put this flat, it's not quite planar on the bottom. These 3 groups around the bottom are getting pushed down by this 4th group. So they're spacing out because the electron groups are repelled from each other. Okay, so this, so no matter how you tip it, those electron groups on the bottom are getting pushed by that 4th group. Okay. So they're, especially if you hold it up to your planar sample, these groups are getting pushed down. Okay. And the bond angles between those are 109.5. Yeah, 109.5. That's called tetrahedral. Okay, we're gonna have, the next one is trigonal bipyramidal. We have 5 groups. So this one, we need another one with a corner post. Okay, we're gonna put 3 around the outside, so like our trigonal planar. 3 around the outside, 1 on the top, 1 on the bottom. Okay. So we need a corner post one. 1 on the top, 1 on the bottom, and then 3 around the middle. Okay, this one is called trigonal bipyramidal because basically we have 2, if you look at this one, basically we have 2 pyramids, trigonal pyramids stacked on top of each other, 1 on the top, 1 on the bottom, if we're looking at the geometric face. Okay, so that, I like this one because you can kind of see the faces, you know what we're talking about. So this one's called trigonal bipyramidal if we have 5 different electron groups. Okay, and then the last one is trigonal, the last one is octahedral. So you just need a square middle. And then there's 1 on the top, 1 on the bottom. Those are called equatorial, 1 on the top, 1 on the bottom. Or axial, these are called axial because it's like an axis. And then the ones around the middle are called equatorial bonds. So I'm going to put 4 around the middle. This is called octahedral. So if you look at the pictures with the triangle boxes, we have an octahedron, we have 8 faces. So if we connected the corners, we would make an octahedron. Okay. So something like that. All right, questions, we got that? So I'm gonna have these out. I think this is helpful to kind of visualize them. So if you need to look at that while you're working on Alex, you can. This is something that you can't use on Alex or on the test. You can use it on Alex. You can't use this on the Alex test. Okay. So you're either gonna have to memorize this or write it on your note card. Okay. All right. So we've got these 5 different shapes. These are for our electron groups. Okay, this is electron geometry. So we have this. Okay, what we're going to talk about next is, I think it's easiest to see on this sheet. Okay, so let's look at water first. How many electron groups do we have for water? So if we draw out our Lewis structure. How many do we have? 3. 1, 2, 3, 4. Okay, so let's draw something with, show us something that looks like water. So we need the tetrahedral one. We need 2 that are hydrogen. Okay. Where is my options? These ones are wrong. Okay, I'm just taking my tetrahedral one. Okay, so I have something that looks like water now. I have 2 hydrogens and 2 lone pairs. Okay. So what would our electron geometry be called? We've got 4 groups. Good, tetrahedral. Okay, this one would be called tetrahedral. But if we're looking at the shape of the molecule, what we need to do is we need to ignore the lone pairs. So we pop off the lone pairs. And then this is called something different. If we're looking at the molecule, we're only looking at the hydrogens and the oxygen. We ignore the lone pairs. And then you can read this chart. We're at tetrahedral, but we have 2 lone pairs. And we're looking at the molecular geometry. This is fit. Okay? So when we're looking at the molecular geometry, we ignore the lone pairs, and we have to figure out what the geometry is based on only the atoms. Does that make sense? So we start with how many electron groups there were. Here we started with 4. We go, oh, that's 4 groups. The electron geometry is tetrahedral. And then if we want to look for the molecular geometry, we pull off the lone pairs. We have 2 of them. We scoot over. We have 2 lone pairs that's fit. Does that make sense? Okay. This is something that's really tricky. Alex is going to tell you, are you looking at the electron geometry? You look at all of the bonds, all of the lone pairs. Or are you looking at the molecular geometry? You only look at the bonds between the atoms. Okay? So watch out. Alex is going to try to trick you by changing those words. So watch what it's talking about. Alright? So take a minute. This is something this seems like this concept people don't understand. So make sure you go ahead and talk to your neighbors. What's the difference between electron pair geometry and molecular pair geometry?
Electronic is like
What were you saying?
But.
Oh, I see.
Your shape there.
Does that make sense to you? But did you spell it? Okay. So, this one we're looking at, slow and this one we're ignoring.
So close your home. Then basically it would just go, right? So what's 2 kilometers? That would just go.
Alright, that makes sense to you?
You just keep on going. Like, let's say, go to, we can just go with the linear.
There's electrons in the
How do you know that?
Alright, you guys got it over here? Yeah, that
Take
is.
it.
Okay, there's a difference over here makes sense.
Yes.
Kind of. Okay. I'm here when you direct us on that. Okay, question for the great back and say the difference. Actually, alright. Okay, we're moving right along. Let's go ahead and talk about how do we do this in real life. So last time we talked about the Lewis dot structure. So the first thing that you do is draw the Lewis structure. Then you're going to count the electron domains, and then you have to decide how they're arranged. And you have to check, is it asking about the molecular geometry or the electron geometry? Okay. So let's go ahead and draw this one. We have sulfur trifluoride. It's a negative ion. Go ahead and draw the Lewis dot diagram. Decide on the molecular shape. Oh, electron geometry. It says electron geometry.
You write down the Lewis dot structure. Triangle.
Yeah. Hey, just be careful. Make sure you draw it out. Make sure you have the right number of electrons. We might have to put extra on sulfur. Oh,
I'll be honest.
oh. But they're negative. This is how one alone here. So that it's that is triple pyramid. I thought that meant they had 5. Oh, trivial pyramid.
16 mark, right?
Where's that? It's a tetrahedron. Oh, but it's yeah, it was called sure.
Right.
Okay. So here, looks like we've got it. Right, let's talk about this. How many total electrons? How many total valence electrons do we need to show? Do we agree with that? Okay. What's your central atom here? Okay. And then we're going to connect fluorine. We got 3 fluorines. Well, that's in fluorine. 2, 4, 6. Now we've got 22 electrons left to show. Where should we put them? Okay, yep, good. We're going to start on the outer atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm just filling fluorine's octet. Now I've shown 18 electrons, or 18 more. How many, is this 12 or 6? We have 6 left. Is that right? This is 4? Okay, thanks. Okay, where are we gonna put those 4 electrons?
I think there's so much.
So we're gonna put the rest of them on sulfur. Okay. Yep, so we've got 2, 4, 2, 4 on sulfur. So now we've shown all of our electrons. Remember, this is a negative ion, so we need to show that this has a negative charge. I'm gonna move my numbers. Let's see. Come on, turn on eraser. Okay, so I have a negative charge. This is a negative charge because it tells you. Okay.
So sulfur can have more.
Yep, it's in that 3rd row. 1, 2, 3. So it could. Fluorine can't because it's in the 1st row. Okay, good. So looking at this, what's the electron geometry we have? How many domains do we have? Electron domains. We've got, let's go through. We've got 1 lone pair, 2 lone pairs, bond, bond, bond. That's how many? 5. Okay, so looking at your chart, what's the, if we have 5, what's that called? Good, that's called trigonal bipyramidal. That means we have 2 trigonal pyramids on top of each other. Okay, so you think it's T-shaped. Can you explain to us how you got that for it? So this is our electron geometry. What if we're looking at the molecular geometry? Good. We have 2 lone pairs here. That's a upside down arrow. Lone pair. 2 lone pairs. 1 here, 1 here. 2 lone pairs. So we just go over. We started at trigonal bipyramidal at 5. So we shoot over. It's going to be T-shaped. Okay. So the electron, the lone pairs are a little bit bigger than a bond. They take up a little bit more space. So they're going to be around the center. So we would put our 2 of these would be lone pairs. So I guess what we would do is we would put them. They're going to be as far apart from each other as they can. The lone pairs are going to go around the equatorial spots. The atoms are going to space out like this. And then if we ignore those lone pairs, it looks like a T for the molecular geometry. T-shape. Okay, thanks. Does that make sense? We got it? So molecular geometry is T-shaped based on our chart. Okay, questions on that? Do you guys want to try another one? Do you want to try on your own in Alex? What do you want to do? You want to do another one? Okay, let's do another one. Okay, this one is NO3 minus. What is the electron geometry, then do the molecular geometry.
I do have.
So is it gonna be 23 electrons?
23. There should only be 18. So what I got is you do N. Plus 5.
It's 20.
Plus 1.
Plus 1.
Redo that.
Oh,
Restate that again.
So
Okay.
5. Wait, 5.
5, where's 5?
5 from the nitrogen. Something that.
Oh, wait, yeah, 5.
Oh, 5. Yep. Okay.
would be around 6. 6 times 3 what? Oh, wait, yeah. 6 times 3.
Nitrogen, yeah.
So you're going to make this
You would have to.
Yep.
I think that's like, and then you have.
Okay, I think we're doing pretty good.
Track.
What would this, how many electrons, valence electrons would we have for this molecule? 24? Okay. What's our central atom? Nitrogen. We're going to bond to 3 oxygens. Okay, we've used up 6 electrons. That's 18 electrons left. We'll put them around the oxygen 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used all of our electrons. We have 0 left. But nitrogen doesn't have an octet. Nitrogen only has 2, 4, 6. So what can we do for nitrogen have an octet?
Bond 2 more nitrogen.
Good. So we just pick one of the oxygens. I'm going to pick this one. This oxygen. I'm going to make this one share with nitrogen. Okay. Oh, the other thing I forgot. Can anyone see what I forgot? Good. Brackets. This thing is negative. I only need brackets if it's a positive or a negative. But this one is. Okay. Questions on this? Does that make sense? This is a simplified version of what's going on. This is good enough for our class. If you take a more advanced class, they will talk more about what's actually going on here. Okay. All right. Oops. Oh, the point of this was, what's our electron geometry? We have how many bonds around our central atom? Good, we've got 1, 2, 3, so it's going to be trigonal pyramidal or trigonal planar.
So it's not.
Oh, remember this is just one spot where electrons live. They're living in the double bond. Shut up. So yeah, double bond is only one electron domain.
Okay, so trigonal with like a ton of lone pairs.
But remember, we're just looking at the central atom for the geometries. We only look at the central atom. So this one is trigonal planar. What would the electron or molecular geometry be? So that's our electron geometry. How many lone pairs are around the central atom? None. So it's going to be the same. Molecular geometry will also be trigonal planar. Okay, questions? There will be one like this on the final. So just one, so it's just one final point, but this is something that you have to learn through those tests, and you should try to learn it for the final. Okay, we're gonna just keep going. And then ask me if you have questions. Make sure you practice in Alex. Where are we? Okay, we talked about the molecular geometry versus lone pair. We tried that. Okay. All right, the last thing I wanted to point out too is that if this is something that you're struggling with, you can use these. I think these are helpful to me to visualize it. Another way you can visualize this is through this PhET simulation, which I'm not sure will work in PowerPoint. Have you done a PhET simulation before? Okay, I'm gonna pull it up outside here.
I didn't go half the time.
There's like 45 questions.
I feel so much.
Sherman had to.
So that's another way to visualize that. If this is something that is you're struggling with, you can look at these different molecules. So water, we can show the bond angles even, okay? We're gonna go with the bond angles in Alex. So if you have lone pair, it gets a little bit different. So maybe don't look at the bond angles here. We can look at what is the molecular geometry for water and what is the electron geometry. And we talked about if we're looking at all four groups, that's the neutral. If we ignore the lone pair and we just look at the molecular geometry, that's called the bent molecule. And we can either show the lone pairs or not show the lone pairs. Okay, and you can turn it around. And there's quite a few different molecules you can look at here. So if that's something that you are interested in, yes.
So the electron domains like move around the atom, or does it like stay in one area on the atom? Or do like electrons just like orbit still like around the atom?
So electrons are like waves. And they look like, let's do this. If you pull up the P table and you look at electrons and you click on something like ruthenium, or let's do iron. So this is showing you the most likely place for those electrons in the 3D orbital. Okay? If I do something like this, if I click on the P orbital, this is the most likely place for the 3P orbital electrons. Okay, so they're not orbiting like they're not just going wherever. Because they have something called a wave function, they are going to make some kind of shape like this. That's the most likely probability of finding the electron in this orbital shape state. Does that help? So they do move, but they move in these specific regions. I don't know. Does that answer your question? Okay. And it is simple. We can simplify it. We're going to simplify it mostly in here, but you can also make it pretty complicated. So if you take like PChem, then you talk about this. Some scientists, that's like their whole job is to try to model this better. Because if we can model where the electrons are, we can predict a lot of reactivity. We can predict new compounds. So this is something that is really useful, but we are not going to go too deep into that. Okay. I'm not sure that helps. Okay. Okay. So we've got like 10 minutes. Go ahead and work on. If you haven't turned in lab 3, make sure you do that. I would also work on Alice Chapter 4. You could also do 2 lab 4. You want to work on it right now?
Let's shut the lab.
No, what? You don't need that.
Yeah, I'm just gonna
It was my turn. Mom said it was my turn.
With the wheels.